Okay, so let's get to some of the basics of USACO. So USACO, for those of you who've never heard of it before, is the USA Coding Olympiad. It consists of 3 questions that you need to solve within 4 to 5 hours. Each question is going to have 10 to 20 test cases, which are just sample inputs that your program will be run on and checked against. For all of those test cases, your program needs to be solved within a certain time limit. I'll talk more about that on the next slide. And in terms of rankings, there are 4 divisions that you can be in. You can be in bronze, silver, gold, or platinum. This workshop will be geared towards the silver level, though I will talk a tiny bit about bronze. So speaking of talking a tiny bit about bronze, in bronze, the techniques that you'll need to use in order to do well in USACO tend to be on the simpler side. So you won't really need to know how to use anything besides extra variables, arrays, loops, and scanners. So a scanner, it's just what you use to get input in Java. If you're using a different coding language, inputs are going to be different. But yeah, just make sure you know how to take the problem input in. And apart from that, that's really all you need to know for bronze. If you find yourself using some more complicated technique, you're most likely doing the question wrong, but at the same time, go for it if you want to. So I also mentioned runtime limits. So in USACO, every single input that your program is tested on, in order to get points for that input, your program is going to need to run in under 2 seconds if you're using C++ or C, and in under 4 seconds if you're using Java and Python. Some questions will have exceptions to this. They might say, for example, for this question, you can take twice as long as normal. But in general, these are the time limits if nothing is specified. Even though those time limits are different across languages, they end up coming to around 1 million operations, no matter what the programming language is. And I'll talk more about what an operation is in a bit, but one final note is that runtime limits almost never matter in bronze. So that's what I meant by if you find yourself using a more complicated algorithm, there's probably a simpler way. Since, yeah, you won't really need to do anything to make your code more efficient for the most part in bronze level. So anyways, the main way that we can, or one of the most useful concepts that's very applicable in USACO is big O notation, which is a measure of how many operations an algorithm needs to run. So an operation in a program is something like an addition, multiplication, storing something in a variable, just in general, any sort of action that's done once. So operations are, big O notation lets us measure the amount of operations that a program is going to need to be able to finish in terms of some kind of variable. And that variable is typically denoted as n, and it's pretty easy to find in USACO questions. For example, the running time of this USACO problem below is going to be in terms of n, which is the number, which is very clearly labeled as n inside of the question. So just some quick notes on operations. So on big O notation, for example, if we had a for loop that runs n times, where n is the variable of our problem, then the running time of that would be denoted as O of n. And in big O notation, we ignore constant time factors. So for example, if I had a for loop that was running 2n times, then we'd still say that the algorithm runs in O of n speed. Now, the reason that we use this notation is that for every single algorithm, the amount of operations that they take tends to be pretty well known. And because of that, just by knowing, for example, the maximum size of n, we can figure out which algorithms we'll be able to use for that question. So for example, in this USACO question below over here, n can be up to 3 times 10 to the 5th, which means, for example, if we're doing a double for loop, and when I say double for loop, I mean a for loop inside of a for loop and not a for loop that runs on 2 times the length of n. But anyways, if we have a double for loop, the running time of that would be n squared, and that would mean that the number of operations that our algorithm would take would be more than 1 million. and we'd be unable to use that algorithm. So just some quick practice with big O notation. What would be the big O notation for the number of operations that this program takes? So let me know in the chat. Yeah, so in this program, we have a single for loop that's running n times. So because of that, it's going to take O of n operations. Now, if we go on to something like this, which is a double for loop or a nested for loop, how many operations would that take? Yeah, so this would take n squared operations. It takes quite a bit longer. So So anyways, here's just a quick list of all of the common time complexities that you will find in problems. So the ones that, so for example, a for loop might take O of n operations, and that would correspond to, for example, looping through an array of size n. And what that means is if this takes O of n operations, and the maximum number of operations that we can have in a USACO question is 1 million, that means that n can be up to 1 million in order for this algorithm to work in a USACO question. So if we look at some other algorithms that take a bit more time, so for example, sorting an array takes O n times log base 2 of n operations. That means that our value of n in a USACO question can only be up to 50,000 if we want to sort an array. If n is more than 50,000, then we're going to have to find a different technique to solve the question, to solve the problem. So here are also some other common time complexities. One very common time complexity in computer science is going to be something related to log base 2 of n, something like binary search, which I'll talk a bit more about that in a minute. And yeah. Oh, and also one last thing, sometimes our problem will be in terms of multiple variables. And in that case, the time complexity might be O of m plus n or something like that. Anyways, let's move on to some commonly used algorithms in Silver. The first one of these, even though it's used a ton outside of Silver too, but I just want to go over it quickly since it is very useful, is binary search. So in binary search, we have some sort of sorted array, and we want to find the index of a particular element inside of that array. So for example, in this example over here, we want to find the index of the number 11 inside of this array, but we don't know where any of the numbers in the array are, or what any of the numbers in the array are. We just know that it's sorted. And we can find the numbers in the array by looking at them. And the binary search algorithm, all that we do in that is that we just constantly look at the middle of the array. So for example, if we look at the value at the middle of the array, we'll see that it's 10. Now, since 10 is less than 11, and this array is sorted, that means that if 11 is inside of this array, it has to be inside of one of these three indices. So basically, we've sort of shrunk down the size of the array where 11 can be to between indices 4 and indices 6. So given that we know 11 is somewhere in these three elements, and we want to sort of cut in half all possibilities every single time we search, where should we search for, where should our next guess for binary search go? Yeah, it should go at index 5, which is right here. And at that point, we'll see that, well, 11 is less than 21, it's greater than 10. So it has to be somewhere in between these two elements. And sure enough, if we check that index, we'll see 11 is indeed in that array. So how many operations do you think binary search will take if we're cutting the array down in half every time? And I know I mentioned this on the previous slide, but it's good to keep in mind how many operations it takes. Yeah, binary search will take log base 2 of the size of our array for, and yeah, that's the number of operations that it will take. For those of you that are interested, here's some sample code. It's all written in Java. If you're interested in other languages, just let me know after the presentation and I can show you how to code binary search in one of those. In general, though, one thing that I should mention is in USACO, if you're ever writing your own binary search algorithm, that tends to be not a great use of time, just because at least in Java, there is a built-in binary search algorithm for arrays that can automatically implement it for you, and it takes a lot less work to do that than to code your own. Anyways, on to another common USACO topic. So another topic that's used in USACO a lot is graphs. So by graphs, or in graphs, what we have is a bunch of nodes, which here I've labeled them 0 through 5, and they're connected in some way. And these nodes and edges can tend to represent some sort of physical thing in USACO questions. So for example, we could imagine that each of these nodes is a farm, and the edges represent paths between the farms. So for example, I can go from farm 0 to farm 1. And yeah, some of the farms, for example, like farm 5, are kind of isolated for everything else. You can't really get to them from anywhere else. But yeah, so in this particular case, the edges are bidirectional, meaning that if there's an edge between 0 and 1, I can get from 0 to 1 and from 1 to 0. There's another type of graph that's a directed graph where that's not the case. For example, in this graph, I might be able to get from node 0 to node 1, but I can't get from node 1 to node 0. And the same is true of all the edges, of all the other edges. A final kind of graph that's somewhat common in USACO, though this tends to occur more in the gold division and higher level silver problems, is a weighted graph. So in a weighted graph, what you're going to have is your nodes. So each node is going to have some kind of weight associated with it. So for example, this weight could represent distance, meaning the distance from farm 1 to farm 0 is 1 unit. Distance from farm 0 to farm 2 is 5 units. And if we were to go directly from 1 to 2, the distance would be 10 units. So graphs like these can also be used a lot in the real world. So for example, you can imagine something like Google Maps. You can think of it as a bunch of nodes representing like intersections, locations, and things like that, and edges representing roads. And there's some kind of time that it takes you to get between each sort of location. And to find, for example, the shortest time it takes to get from location 1 to location 2, you would want to just take the shortest path, and actually that ends up meaning that you have to pass your node 0. The algorithm that you can use to do this is called Dijkstra's algorithm. If you're interested in that, feel free to read up on it later, but I won't be going over it in detail here. So anyways, let's head back to our original graph, where we were talking about farms and them being connected. So one kind of natural question that we can ask about these farms is whether I can get from one farm to another farm. So for example, let me ask you, can I get from farm 0 to farm 5? Okay, but can I get from farm 0 to farm 4, let's say? Yeah. Anyways, so we'll talk more about on that later, but first, I just want to take a quick aside and talk about how we'd actually represent these graphs in a coding question, since that actually ends up being one of the most important parts of graph-based problems. When it comes to storing graphs, we obviously, in a computer, we can't really store it visually like this with a bunch of circles and lines. That would be quite inefficient. So our two options are, so the first of our two options is an adjacency matrix, where we have a giant 2x2 array that stores the connection between nodes. And so for example, in this particular array, for a normal graph, it would just store zeros and ones. So for example, if I look at row 1, column 0, since that is a 1, that means that those two nodes are connected. And actually, this adjacency matrix represents the graph on this slide. So for example, we'll see that nodes 2 and 3 are connected since there's a 1 there. And also, for example, node 5 isn't connected to anything, since in this adjacency matrix, with every other node, there is a 0, meaning there isn't a path to those other nodes. The advantage of an adjacency matrix in USACO questions is that it's really easy to check if an edge exists. So for example, if I want to check whether I can go from node 1 to node 0, I just look at array of 1, 0, and I'll see, oh, that's a 1, I can. Another useful thing about adjacency matrices is that it's very easy to to use them to store both weighted and directed graphs. So for directed graph, you would just decide to only have a 1 on one side of this array. So for example, in a directed graph, let's say if I could only go from node 1 to node 0, I would keep this 1 here, representing I can go from 1 to node 0, but this cell over here would become a 0, since I wouldn't be able to go from node 0 to node 1. For a weighted graph, we can also just, instead of storing zeros and ones, we can store the weights. So that's also pretty easy to change. Now, one quick question. In an adjacency matrix, how many operations does it take to loop through all of the nodes that I am connected to? So for example, if I'm at node 0, how many operations does it take me to go through the rest of these nodes and sort of branch out to the ones that I'm connected to? Yeah, so you guys got it. It takes n operations, assuming this is an n by n array, which is pretty inefficient. Aaron, you would need 1 to check if an individual edge exists, but in order to go through all of the edges, you actually need to loop through this entire array. So it takes n operations. Yeah, since we're just really doing a for loop. So another problem with these adjacency matrices is that how many operations does it take to create the adjacency matrix? So it turns out, since we have a 2 by 2 matrix, there are going to be n squared entries in here, which means, yeah, it takes us n squared operations just to create this matrix, which means, for example, if we have 1,000 nodes, this would already be something that we can't really do inside of a USACO question. So there is a solution that is a lot more space efficient called adjacency lists. So the idea for adjacency lists is that instead of having an array that stores zeros and ones, we only really need either the zeros or the ones in order to have all of the information about this graph. Because, for example, this list, so basically we have a list of nodes that we are connected to. So for example, 0 is connected to nodes 1 and 2. And we know which nodes it's not connected to because those nodes are just not inside of the list. So we can store this either as a list, or it can be slightly more efficient to store connections between nodes as a hash set if you're working in Java. There are similar data structures in other languages too. And these lists are really good for sparse graphs. And what a sparse graph is just a graph that has a lot of nodes, but not a lot of edges. So a graph where most of these numbers are zeros in this adjacency matrix. And in this graph, if we wanted to loop through all of the connections, then we only need to use as many operations as there are connections. The downside of adjacency lists is that they're a bit more annoying to use in weighted graphs. For directed graphs, though, we can still have an adjacency list pretty easily. So for example, I would just say I can get from node 1 to 0, but I can't. in order to say I can't get from 0 to 1, I would just remove this 1 from the adjacency list of node 0. For weighted graphs, it's a bit more complicated, and we actually need to use hash maps in order to go through them. So a hash map, it's just the way that would work is we would be mapping this node to its weight. So for example, in node 0, its adjacency list would actually be a map that stores, let's say, node 1 is mapped to the weight of 5, and node 2 is mapped to the weight of 3, let's say. So anyways, going back to our question of searching graphs and checking if two nodes are connected, the general idea for what we want to do in this kind of algorithm is we have some kind of starting node, and we want to find if some kind of node or value is connected to it. Alternatively, we might also want to do something with the nodes. So for example, we might want to find a reference to the node, or a reference to all nodes connected to it, or to do something with all nodes connected to it. And that's actually pretty similar to checking if two nodes are connected. And that's called a flood fill algorithm. So finding all of the nodes that a node is connected to. But anyways, yeah, our general searching algorithm problem is just going to be searching if two nodes are connected. So as I asked you before, node 0 and node 5 here aren't connected. And we can see that pretty easily. But I feel like when we do this as humans, looking at this picture, we're almost sort of cheating. Because when we ask if node 0 and node 5 are connected, we can pretty clearly see, well, node 5 isn't connected to anything. There's just giant empty space here. And because of that, node 5 isn't really, like, we can tell really easily that it's not connected. But for a computer, things are a bit harder, because we don't actually know all of this graph until we manually go through all of its nodes. So let's try thinking of this like a computer and try finding if nodes 0 and node 5 are connected. So if I start at node 0, what's the first thing that I should do in order to, or what's the only thing that I can really do to check if node 0 and node 5 are connected? Yeah, the only thing I can really do is check the nodes that 0 is connected to and branch out until I either reach 5 or I don't reach 5. So for example, firstly, I might see that, well, oh, 2 is a neighbor of 0, so I can branch out to 2. And then continuing to branch out, I might see that 4 is a neighbor of 2. And it turns out 4 doesn't have any neighbors. So if we continue going to the neighbors of 2, we'll see 3 is a neighbor of 2. And then finally, going back, we'll see the only neighbors of 0 are 2 and 3. And it turns out there are no more connections in this graph. That's a great question. It turns out this graph is actually slightly different from the one in the previous slide. So I changed it up a bit just to make it a bit harder. So now I can reveal the full graph if you want, and it looks like this. So node 1 is connected to node 5, and the rest are sort of interconnected. So there are actually two ways that I can do this searching algorithm. The one that I did, where I went from 0 to 2, then 2 to 4, and 2 to 3, is called depth-first searching, where I branch out to a node, and then I branch out to all of that node's children, and so on. Children or neighbors, either one can work as a word to describe nodes that you're connected to. The advantage of depth-first search is that it's really easy to implement recursively in coding. But yeah, but the algorithm that's slightly more intuitive is a breadth-first search, where I would first go to all of the neighbors of node 0. So I would see 0 is connected to 3, 0 is connected to 2, and then I would branch out from those. So breadth-first search is has some other advantages over depth first search. So for example, using breadth first search, I can also find the shortest path between nodes, and I can also find the distance between nodes in terms of like the number of connections I need to get from, for example, 0 to 4. However, breadth first search is a bit harder to implement, and it requires queues. Also, answering the chat, yeah, as Zubin said, you don't really have a better way as a computer to check things that nodes are connected to, because you don't really, like, the only way that you can get more information about connections is by sort of, yeah, it's just by searching through the graph more, or by looking through all of the neighbors. Yeah. There are some ways that we can try to amortize this cost over multiple nodes. So for example, if I wanted to find the set of all nodes that 0 is connected to, I wouldn't run this algorithm on nodes, on all of nodes 1, 2, 3, 4, and 5. I would instead just store all of the nodes that I'm able to branch out to from node 0 in a set, and that would end up being much more efficient. However, for a single node, we don't really have a better option, unfortunately. And one final thing that I need to mention about all of this node branching out is that in these nodes, as humans, it's pretty intuitive, like, oh, if I went from node 0 to node 2 to node 3, I don't want to go back to node 0 after that when I'm searching, because we've already been to node 0. But even though this is pretty easy to do, like for us humans, in a computer, we need to make sure that we don't end up going to the same node twice. And in order to do that, we need some sort of array list or set to keep track of all the elements that we've visited so far to make sure that we don't visit them again. So on to some quick sample code for depth first search. So depth first search is pretty easy to implement recursively. But also, even before that, I'm just going to just a quick explanation of this code here. So in this code here, I've chosen to represent nodes using adjacency lists, since those are more efficient in most cases. And yeah, so typically the way that you do that is you would create a separate class to store your nodes. And then here I've created an array of all of my nodes. You don't necessarily have to do things like that, but that is one way to store nodes. And then, yeah, so in the depth first search algorithm itself, all you really need, the few main things that you need to do are make sure to create a set to store all of the nodes you've been to. And then for the depth first search itself, it's a pretty simple algorithm recursively, where for every single node, you just call the recursive function on all of its neighbors. And then, yeah, you also have some checking to see whether nodes have been visited, but overall, pretty easy to implement. For breadth first search, actually, just a quick note. The reason that this ends up being depth first search is that in a recursive algorithm, if I go from, for example, node 0 to node 2, the algorithm for node 2 needs to fully execute and finish executing before I can go to any of 0's other neighbors. So because of that, I end up going through all of 2's neighbors before I end up before I get back to node 3. Breadth first search is a bit more complicated, and the reason for that is we need to somehow get around this going through all of 2's neighbors before I go through all of 0's neighbors. And the way that you can do that is by having a queue to store all of the nodes that you want to visit. And that way, what's going to happen is that after I branch out from node 0, I'm just going to, or actually, let me go back to the graph. So after I branch out from node 0, I will add 2 and 3 to the queue of nodes that need to be checked. And after that, let's say if I go to node 2, node 4 will also be added to the queue. But because in queues, what happens is that the elements that are added last sort of stay last. 4 is going to appear after 3, and I'm going to end up going to node 3 next. Yeah, just actually, some quick. So just a quick explanation of what a queue is for those of you who might not have seen it before is it's just a data structure where so as I add on elements, they're added to the end of the queue. So it's sort of like a list in that sense. So for example, I might add on node 2, then node 3, then node 4. And what the queue does is it just, every time we take the first element in that sort of list, and then we get rid of it, and then we loop to the next one when we're done with that. Oh, just a second. Yeah. So in breadth-first search, we just use a queue so that we're always going to the most recent nodes, or the nodes with the fewest branches away from us first. So any questions about graphs? All right. If no one has any questions about graphs, I want to move on to one final algorithm that's used in USACO a lot called the sliding window algorithm. So sliding window is used to find the sums of sections of an array that meet specific criteria. Now, that sounds really fancy, but let's go through a specific case first. Specifically, let's try to find the smallest sum any subarray of length 4 has in this array below. And I've highlighted all the subarrays of length 4 here. So I'll give you guys a minute or two. What is the smallest sum? I'm seeing some different answers. It is 13, yeah. So my real question though is how, so yeah, the smallest sum is 13, and the way that we can figure that out is just finding the sum of all the subarrays. So for example, the top one, it has a sum of 20, then 18, then 13, then 15, and we can see, oh, 13 is the smallest of all of these numbers. But the real question here is, how did you find the sum? So I'm assuming what most of you did is for every single array, you added up all of the numbers in it. So for example, in this top array over here, you might have added up 3 plus 7 plus 6 plus 4. And then you would reach a sum of 20. And then here you might add 7 plus 6 plus 4 plus 1, giving you a sum of 18, and so on. And yeah, that way you might have gotten all of the sums. However, it turns out there is a much faster method that we can add up all of the numbers in these subarrays. And the reason for that faster method is that in this sort of window over here, you'll notice that a lot of the additions that we're doing can be reused from one subarray to the next. So for example, in both this array and in the next one, I'm going to have to add up 7 plus 6 plus 4 in order to find the sum. In fact, the only difference is that, so let's say if I know the sum of this subarray is 20, the only difference between this sum and this one is that I'm adding on 1, because 1 is at the end over here, and I'm subtracting 3. So yeah, because 3 is no longer in the array. And then using the sum from this second subarray, I can find the sum of the next subarray by adding 2 and subtracting 7. And that way, I can actually find all of the sums of all the subarrays just a bit faster. In this particular example, it ends up not being that much faster. So for example, here we're doing 4 additions, or we're adding 4 numbers each time for a total of 16 additions, whereas here it's 13. So it might seem like a minor cost saving at first, but turns out it's actually a lot more than just a small decrease when we get to larger arrays. So in order to talk about that, let's just generalize this problem a tiny bit. So let's say we have an array of size n, and we want to find the smallest sum among all subarrays of length m. If we were to use method 1 over here, where we would use a for loop to add up all of the elements in each subarray every single time, what would be the time complexity of that algorithm? So turns out the time complexity of adding up all of the elements in each subarray is going to be O of n times m. The reason for that is that we're doing a for loop on m elements. So if it's for loop that over there times roughly n subarrays. The time complexity is actually, I think, like if you were technically to find the number of operations, it would be the number of subarrays is O minus m, or sorry, n minus m plus 1. But that m minus m plus 1 part is just, we can ignore it since it's insignificant compared to the main time complexity of n times m. So yeah, in general, we have roughly n arrays here that we're going to be adding up, each of them of size m. So we're doing a total of m times n additions. Now, let me ask you another question. So if we were to use our second method over here, where we reuse the sum from the previous question, what would be the time complexity of that? So that question's a bit harder. And remember when you find your answer to ignore constant time factors. Do you want a hint? So, okay, just a quick hint for this question. Finding the exact number of operations that this is going to take is pretty hard, actually. It's not something that's easy to do. But in general, but it's actually a lot easier, at least for this particular problem. Instead of like thinking, here I'm doing 4 operations, or here I'm doing 3 additions, here I'm doing 2, or here I'm adding 4 numbers, here 3, here 3, here 3, and adding that all up. It's a lot easier to think in terms of the number of operations is always going to be less than something. So in this particular case, if we think about it, it's every single number in this array is going to be added once and subtracted once, at most. Some numbers are might be added more than once, or sorry, no, some numbers might not be subtracted ever. So for example, 8 over here we're never going to end up subtracting that. And some numbers might not, but yeah, anyways, every number actually ends up getting added. But in general, it turns out the time complexity is just going to be, it has to be less than 2 times n. If you want to get all technical about it, I think it would be 2 times n minus m plus 1, since all of the numbers, or sorry, just minus m, since all of these numbers in the last sort of subarray are never going to end up being subtracted. However, in big O notation, we ignore constant time factors. And also another convention is if you have something like a minus m, you also ignore that in big O notation, since the maximum time complexity is still going to be around 2 times n. So, actually I said 2 times n, I meant to just say O of n is the maximum time complexity, since we also ignore constant time factors. So yeah, it turns out time complexity of reusing the sum from the previous subarray is just O of n. So you'll notice we've actually managed to get rid of a factor of m in this question, which that can be huge. So depending on the problem, if m is, let's say, 100, this reusing sums is 100 times faster. And in general, the larger your subarrays get, the better this will be. So one thing that we do need to do is sort of formalize the sliding window approach, and then also generalize it a bit. So for this particular problem, the sort of algorithm that we're running, and by the way, method 2 over here is referred to as, or I'm going to refer to it as the sliding window algorithm. Sorry, I should have explained that earlier. But anyways, so the general idea behind our sliding window algorithm is that we're constantly going to keep track of sort of the left and rightmost sides of our section. So for example, in our array of size 7, we have a bunch of numbers. So I forget the exact numbers, but let's say we have 0, 1, 2, 3, 4, 5, 6. So let's say those are 7 numbers. What we do in our sliding window algorithm is all we'd really do is keep track of the left and right sides of our window, which is the subarray that we're currently looking at. And to get to the next subarray, we need to just increment both of these sides. So we need to move this pointer over 1, and we need to move this pointer over 1. And we need to add the element over here where our right pointer is now going to be, and subtract the one where our left pointer used to be. In practice, it turns out it's a bit easier, or it takes slightly less code to do this if we don't advance our left and right pointers simultaneously. So in practice, what might happen is that when we start in the array, we would have both our left and right pointers start at 0. And then we would move our pointer for the right side of the array over by 1 until we have the length that we want to have. So in this case, we would move the right pointer away and add on the elements as we, and add values as we move it, until the left and the right pointers are 3 indices apart. And this has the advantage that if, for example, we were to start our pointers like this, we would need some kind of for loop to sum up these to find the sum of the first subarray. But if we start both of our pointers in the same spot, we actually don't have to do that, and it ends up being a cleaner solution with less code. So yeah, we just move along our right pointer until it's over here. And by that time, we will have calculated the sum of our window. And then after that, we can just move the left pointer, and then our code to move the right pointer will move the right pointer again. So I'm sure many of you are wondering what this actually looks like in practice, coded up. And it looks something like this. So we can start both our left and right pointers for our window to start at 0. And we're also going to just have a variable to keep track of the sum. And of course, a variable to keep track of the minimum sum so that we can find the minimum and actually solve our problem. The general idea is that as long as the right pointer is in bounds, we're going to just keep on moving it up as long as it's, or until it's the proper distance apart from the left pointer. Once it is the proper distance apart from the left pointer, we're going to know the sum of that section because we'll constantly have incremented our sum as we were moving that right pointer up. And then we can check if this sum is less than the minimum sum. If it is, we know that is the minimum sum. And otherwise, we can just, and then, yeah, once we have reached a subarray of length 4, we can just take away the element at our current left pointer, increment the left pointer, and then we will sort of be left, and then this if statement will run again, the window will be back at the proper length. That might sound a bit confusing, and it's definitely not as intuitive as the find the sum of the first array, subtract the first element, add the last element. However, it turns out that this code over here is a lot more generalizable than that approach. And the reason for that is that this code over, or in a lot of sliding window questions, we won't necessarily be asking you to have a window of a fixed length. For example, we might want to have we might have a sliding window problem where we want to check that, where we might want to find a window such that the difference between the first element in our window and the last element in our window is 5 or something like that. So if we have an array of like 1, 5, 7, 4, 0, we might want to take all windows where the difference between the first and last element is less than 0, or sorry, is less than 5 or something like that. Anyways, more on that later. Any questions about sliding window implementation? All right. So finally, let's go on to some practice questions to see which of these to see how these algorithms might be applied in a real USACO question. So I know there's a lot of text here, but let's go through some USACO questions. So first of all, we have this question from USACO 2016 Silver from December, where we have N cows that are capable of broadcasting messages to each other and yeah, they're only able to broadcast over a certain distance. But those distances vary between cows. For example, if cow 2 is closer to cow 3 than I am, I might want to broadcast my message to cow 2, and then cow 2 will broadcast the message to cow 3, and that way the message will be eventually broadcast to cow 3. So the question, it's just sort of asking if I have a starting cow, or yeah, from cow 1, what are all the cows that you can actually broadcast the message to? If you want, feel free to read through the whole text. My summary is definitely not perfect, but yeah, which algorithm do you think would be most applicable here? Ooh, and I see we're already getting some answers. If you want, perhaps it would help if I sort of draw out what this question might look like. So, oh dear, there's not a ton of space here. Well, let's say we have a cow 1 that has a broadcast distance such that it has a broadcast distance of 3, let's say, so cow 1's over here, and then we'd have like cow 2 is here, cow 4 is here. And in general, the idea is that the cows that we're able to broadcast to, we can actually use those as edges in a graph. So for example, cow 1 might be able to broadcast to cow 2, but not to cow 4 since it's too far away. And then cow 2 might be able to broadcast to cow 3 and to cow 5 over here. And the general idea is we can form a graph using these talking distances, and using those graph edges, as Sophia said, we can use depth first search to figure out which cows we're able to talk to. Or more specifically, I guess in this case, the number of cows we're able to talk to, but it's a similar process. Anya, as you said, we actually can use breadth first search too, if you want to. In general, the breadth first search, it takes longer to implement, and it's a bit more difficult than depth first search if you're not very familiar with it. So depth first search tends to be the algorithm you want to go for in questions like this. So let's go through one more question. So in this question, we have a cow with a bunch of diamonds that all have some different size. And those sizes, you want them to differ by some maximum, or those sizes can differ by some maximum amount, but within that constraint, you want to find the maximum number of diamonds that you can pack in 2 cases, such that all the diamonds within a case are pretty similar. And down here, I just have an example of what the sample input might look like in terms of here are the weights of all our diamonds, and and 2 diamonds can have a distance of at most 3. Or a difference in weights of at most 3 for us to include them in the same case. So yeah, Sophia, as you said, it turns out sliding window is the way that we can solve this question, but it's not immediately clear how we would use sliding window. And actually, it turns out there's a second part to this problem that we need to do. And our hint for that second part is that n is less than or equal to 50,000. So in general, if you ever see something where it's like less than or equal to 50,000, or where n is less than or equal to 50,000 in a problem, that means that the algorithms that you're able to use have to have a time complexity of at most n times log of n, times log base 2 of n. In general, you will always be using some algorithm that has that maximum time complexity. And in this particular case, one algorithm that has a time complexity of log base 2 of n is sorting an array. And it turns out that the first part of this problem is we need to sort this array of all of our diamonds. And then after the array is sorted, it's a lot easier to figure out which diamonds are close to each other distance-wise. And at that point, we can actually use a sliding window algorithm. In this particular question, the way that we would figure out the maximum number of diamonds that can fit in each case is we would say, let's say, for example, so after we've sorted the array to something like this, we would say, for example, if 1 is the smallest weight diamond, or if the diamond of weight 1 is the smallest weight diamond that I have in a case, what is the maximum number of diamonds that I can have in that case? And it turns out for 1, the answer is you can only fit that diamond in the case, since the next biggest diamond has size 5, which is too big to fit in the case. At that point, we would see, okay, if the smallest diamond is of length 5, or of size 5, then the maximum number of diamonds we can fit in the case is 2, since we can also fit in the second diamond of size 5. If this size 5 diamond is the smallest diamond in the case, we can only fit in 1, since we're just looking to the right in the array, and the next number 9 is too big. And sort of continuing, if 9 is one of the diamonds that we put in the, or if 9 is the smallest weight diamond that we put in one of the cases, then the maximum number of diamonds we can have in that case is going to be 3. Here it's going to be 2. And here it's going to be 1. And then finally, here it's going to be 0. So this right here is just sort of, this is just from our example problem where we have the maximum distance is, or the maximum difference in weight is 3. And from this point, we would see, well, clearly the most we can fit in one case is 3. So we probably want to include that. And then this 2 is part of this array of 3. So actually, if we're including so if we want to include these 2 diamonds, or sorry, these 2 diamonds have already been taken up by the case with 3 diamonds in it. So then we want to take the other case, or the other possibility where we would get 2 diamonds in a case, which is over here. And that gives us a total of a maximum of 5 diamonds among the 2 cases. It's definitely a bit more difficult to see how sliding window would be applied here, but it turns out the way that we do it is we would just slightly modify our code from before. So we would set our left pointer and right pointer to here, and then we'd see, oh, well, if I move my right pointer here, 5 is too heavy in order for these 2 to be in the same case. And so because of that, I would know that the sum here is 1. If I move, and then at that point, I would move my left pointer to over here, and so on. And that's how the sliding window algorithm would be implemented. Any questions about that? It's definitely a bit harder to wrap your head around this one. All right. Well, if no one has any questions, well, feel free to stay if you do have any questions on any of these algorithms or just USACO Solver in general. But if you don't have any questions, thanks for coming. That's it for now.
Thank you.
Oh, Zubin, sorry, I forgot to respond earlier. USACO, it starts in December, and it runs for 5 months consecutively. So I think it's December through March, I think. Let me double check. Sorry, they only have 4 contests. So it's, yeah, there are 3 contests in January. So there's a contest in January, 1 in December, 1 in February. And then in March, you have a kind of special contest called the US Open, which is just, it's similar to the other contests, but the questions tend to be harder and you have an extra hour to work on them. Oh, I believe normal USACO is 3 hours, USACO Open is 4 hours. Any questions or? All right.